George has raised the interesting question of where might the JVM be going and how fast also. Not too fast, not too slow is the answer I hope to give, but of course that has lots of details. We meaning Brian and I, wish to talk to you for a little while about where the VM can go. We want to talk both about what the VM how the VM ought to change. In other words, what's most useful to the people in this room and other Java community stakeholders, and also some specific things that we think are coming up next in the pipeline. There's a very small number in this talk of speculative things. I haven't named all the crazy things that we're thinking about doing, but I've tried to give you a flavor of what we're thinking about, and certainly about where we think the major investments are 9, 10, and 11. So let's start by looking at the the slide that says that you don't take too seriously what I say. This is between us nerds, and so the process of getting to somewhere where you can actually hold us accountable to doing a particular piece of work is very long and arduous, and that's not part of today's agenda. Although George suggested it's quite, it's rather friendlier than you might have feared. The developers do get to speak into the evolution of Java, and that's one of the reasons we're all here, is so we can speak together. If I say something that doesn't serve your needs, I'm curious about it, within limits, of course. So let's go back and do a little walk through history. This is the JVM vision as of almost 20 years ago, that we're building a multi-language runtime, which is kind of a surprise, but it was something that seemed useful for reasons I'll try to pick at a little bit later. It seemed useful to the original designers of Java to do a runtime that wasn't just an exact fit for the language that they were doing at that time. One of the evidences that worked was that we were able to evolve the language significantly within the first 10 years or so without changing the runtime very much at all. That eventually ran out of steam. But in the beginning, we did want something that would allow multiple languages to run, and even we expected we would be making some changes, bounded extensions to the JVM architecture so that we could support even more languages, and as it turned out, our own language. This intention to make the bounded extensions is reaffirmed in the most recent version of Java SE, the JLS. And thank you, Alex, for preserving that intention in that book. Let me say a little bit about where a specific area that we were designed a little bit into a corner. This is all familiar to you who've been to this conference a bunch of times and have seen talks about invoke dynamic. The invoke instructions in the JVM bytecode as of 1995 or earlier had certain characteristics that unintentionally limited them to be most useful for Java, but not so useful for certain other, like Smalltalk type applications. So in particular, the linkage is static. It can't be redone. There's no user level monomorphic inline cache or any of those sorts of good tricks. The dispatch is single dispatch, usually single inheritance, but with a little tricks for a little bit of multiple inheritance in the standard ways. But there's certainly no double dispatch or anything like that. No generic arithmetic with dynamic types like some platforms have. There is the arguments and return types to methods are extremely fixed according to static typing rules, which is kind of not what you'd expect to see in a very dynamic platform. And from my point of view, one of the worst problems that's given us pain over the years many times is that you can only return one thing at a time. And so you can't return from a query a result and a Boolean which said whether that result was present. That's one of the common ones. You also can't return a 128-bit int, even if you're willing to break it into 264-bit ints. you got to put it sideways in the memory and then return a pointer to it. This is a serious pain point for API designers and language implementers. The workarounds exist, but they're hard. They have simulation overheads. So let's fix some of that. As of 2009, we started working on JSR 292. We have the details of it are familiar to you. I'm not going to go over the whole slide here. It's going to be posted for you to look at if you want to make a reference to it. The essential point I want to make is that the pain was lessened as the Nashorn developers described yesterday. It was suddenly easier to do new kinds of code shapes without having to always work around the limitations of the old invoke instructions. I particularly like the Nashorn de-optimization trick where you package together a whole bunch of locals into a frame state in one instruction. And however would a JVM have that one instruction pre-calculated in it? Well, you can imagine that now in retrospect, but no one would have invented it up front. But given a flexible invoke dynamic instruction, the Nashorn people were able to adapt a very specific instruction to their needs because they were able to define it. There is still a problem with that last point with multiple return values. You still can't do that because we don't have signatures with multiple return values. So we have some thoughts about that, however. In any case, the current Java language specification says we made good on the progress to do the bounded extensions. Hurrah! And we're not done, which is the good news for today and for this year. This is my favorite knife. This is what I carry in my pocket, my Swiss Army knife. It's got one tool for just the right set of tasks that I like to do. If I need to saw a branch in my yard, or if I need to cut my nails, or if I need to open a bottle of wine, it's all there. It's neither too much nor too little. And for me, that's kind of a metaphor of what a good runtime is like. It doesn't tell you what you're going to do. It's a multitask implement, but it's there friendly and ready in your pocket when you want to do any of a wide range of ordinary tasks. So in that vein, let's go find some more pain points. Let's find some more things like invoke to fix. Let's find places where, for example, the language unintentionally dictates too much of the JVM design, or where the JVM does not anymore or never did accurately reflect what stock hardware does, or where the JVM has some other cost that it imposes. And I think there are a number of places where we can find these pain points and remove them. We want to be able to, of course, keep simplicity and compatibility for both the old users and the new users of the new functionality. I have some more thoughts about that later. Here's the big slide that kind of gives a 80% view of the big pain points. I think there are probably some that we could come up with in this room that are left off the slide. But there are, I'll go down it quickly, and I'll leave you to look in more detail at the online copy of this and wonder what I meant by it. But names, they used to be required. It used to be required that they be valid Java identifiers. I don't know if you remember that. How many of you remember the JVM putting that requirement on byte-coded names? Yeah, a couple, yeah. Now they can be almost any Unicode sequence of almost any length, which is very, very handy. There's more we want to do, because names beyond a few hundred characters really want to have a substructure. Flattening names is kind of a footprint-heavy move. But that's something we can talk about in the future. But at least what we did as of JSR 202, Java 1.5, was to allow arbitrary Unicode inside the names. That's a good example, although a simple one, of removing a pain point that was just putting unnecessary burdens that came unintentionally from Java on language implementers. The invocation modes we already talked about. That was fixed in 1.7 to a large extent. There's more we can do with invocation modes. We still don't have tail call. Guy Steele reminds us of that every year or so. And there are things that we could do with scheduling threaded execution of basic blocks through tail calls that would be more robust and more bug-free than our current workarounds, which involve occasionally blowing the stack, just at the worst time when you get a bad data pattern due to scheduling in fork join, for example. It's something Doug Lee pointed out in this forum maybe 2 or 3 years ago, and we regrettably haven't fixed that yet. That's one of those things where the customers need to ask more loudly, I think. Anyway, tail call is kind of an orphan child. Type definitions can be done by loading classes, but they're shaped very much like Java classes. So if you want a type definition that's very different from a Java class, then maybe there's some pain points there that we can fix. And likewise with application loading, if your application isn't a set of classes, then there are some simulation overheads, which we're looking to address with Project Jigsaw. Concurrency is done the old-fashioned way with threads and with object intrinsic monitors. Well, those sort of are orphaned nowadays, aren't they? There's the Doug Lee concurrency package that's much better. But I think we need to do something long-term with better threads and monitors. We put a down payment on that in 8 with streams, which is abstracted iteration that can be fork joined, and as the AMD people have proven, can be GPU'd also. So that's progress. Mutability is still an issue. We don't have immutable arrays yet, and there are safety and synchronization problems with that. We have some proposals coming up. There's a talk later today on this with var handles to talk about some of the things we're thinking about there. Data layout is a problem. Not all, the JVM isn't the only way to, the JVM's tactics are not the only way to lay out data, and sometimes you need other ways that are either denser or friendlier to pre-existing libraries. So for that, we're looking at Project Panama and new arrays, value types, FFI. And likewise, with native code libraries, like with native data, JNI is the current way to get to it, but JNR is a much better way. So we have known better solutions than JNI, and we're aspiring now to get them into our ecosystem in a central position. Thanks to Charlie Nutter and Wayne Meissner for that. So that's the whole talk. Really. The rest of it is elucidation, although I have a lot to say about value types. I hope you're up for that. One thing here is there's probably missing pieces on this slide, and you're going to have to help us fill in the missing pieces, right? That's why we're here. You might want to ask the question, all right, is this really about other language implementers, or is it just 4-letter words that start with J? George also addressed this question, why do we care about being so community-minded? Why don't we just get on with our own business and make whatever money we can off of our customers? And the answer is, as George said, it's not just the whole community, but also very specifically, we feel specific benefit at Oracle from being able to have an awesome language that we can improve directly, that we use in our own products, and that performs well, that works well with the brains of our developers, it's easy to train on, and that a whole community is liking also. So that means we have, in order not to break that good state of affairs, we all work together to keep Java being well-designed and easy to learn, something that people can train on well. And I think this involves not freezing the language nor growing it with rapid abandon, but a process that Mark Reinhold once called selective sedimentation, slowly taking the floating features out there or the ideas that make sense and binding them down to the design of Java itself. So there might be way out languages that have crazy experimental ideas, Some of them are probably going on 10 years now in the Java ecosystem. And Java will slowly take some of their ideas and, where it makes sense, work it into the language itself. But my point of view as a JVM architect is I want the JVM to make it easy for that sedimentation to occur. And this is a fundamental reason why the JVM needs to be friendly to other languages, not just a Java execution engine. The JVM is oriented towards these future languages. It's also oriented towards hardware and future hardware. In other words, when we look, there's this funny circular thing going on between the hardware and the software people. The software people are throwing more and more workloads at hardware, and hardware is saying, oh, well, how are we going to make a cache for that, or how are we going to make a transaction for that? Oh, we've got to widen our vectors again. Those software people are really demanding it. And oh, we have to execute this really horrible code they're throwing at us. We'll do some branch prediction and jump over the bad parts quickly so we can actually execute what they're asking for. I don't know how many of us spend time with hardware folks, but that's kind of what it looks like from their world. And so the hardware, which has these, like Intel chips, have these really strange features in them that software people don't understand, but they're there for the software people. They're there to handle the artifacts that the software people accidentally put into their code streams. As a result, hardware has this funny coupling to what we do as software people. And, but it's also moving in directions that are dictated by physics, speed of light and capacitance and heat flow and things like that. So it's a compromise between what can be crammed onto a chip and run really fast and parallel and low power and what the software is asking it to do. Where the JVM comes in this is we have the chance as JVM people to say, okay, we can virtualize so that we don't have to run on one particular hardware, but we can selectively adapt lots of new features. If the vectors get wider, we can do that. We can transparently change our, say, stream API, stream internals, not API, or our compiler tactics, and make use of those new hardware features. Transactions, for example, are really interesting and I think important and a harbinger of new ways of looking at memory. The Haswell TSX stuff. So the JVM also evolves in a circular way, affecting and being affected by what the hardware people are doing. And that means that is a very concrete reason why it can't be just language driven. It has to aim at being able to express what hardware does well. In the end, what we get from aiming not just at Java per se, but at languages, and not just at one particular hardware platform, but at where we think the vector of future hardware is going, what we get is something that a lot of brains, including those in this room, are willing to spend time thinking about and improving. So making this system, making the JVM attractive and widely applicable means that we get lots of good colleagues to think about how to make it better. And I think that's the fundamental value proposition for a multi-language VM. So briefly, a few ways that we can extend the VM rightly is by not breaking old bytecodes. We have this funny trick where if the class file format is of a certain number, even if there are new bytecodes floating around, we have the class loader ignore those new bytecodes for the old class version number. And so that gives us a very, very clean and disciplined way to support old class files, old code, and still support new features coming into the VM. We want also to have the new features not interfere with the old ones, so you don't have to choose between the old way and the new way. In fact, the new mechanisms should be supersets of the old ones. If we introduce new arrays, which we intend to, we don't want them to displace the old arrays, so you have to forget everything you knew about arrays and throw away all of your array-based APIs and make new ones, right? That would be almost a language change. So part of the intellectual puzzle of doing JVM evolution is finding a place for the old features that weren't quite right now and still giving them a place of honor, but in a larger population of useful features. And there's this word I want to use called categorical. I want to describe a well-conceived feature in the JVM as categorical when it fits to the entire category of the hardware and the family of languages that are going to compile to the JVM. In other words, it sits between the hardware and multiple languages in such a way that it does not artificially constrict or transform the connections that need to be made between the language and the hardware. My knowledge of category theory is vague at best, but it tends to focus on the essential structure of, say, ordered pairs or tensor products, and to say, okay, what are the essentials there? If we make sure that we have no accidental limitations in our mathematical structure, what's left that's essential that you can't do without? That's a good mental exercise for JVM design. It means things like, if I'm going to load methods, I probably shouldn't load methods that only come from the Java compiler. In fact, maybe I should load methods that are larger than an arbitrary 16-bit limit. Right, so there's a method size that I would claim is not essential to the category of virtual machines, that there be a method size limit. So we want natural, not unnaturally contorted mechanisms. That's about the best I can do to describe that idea at present. So, two big initiatives that are just started, which are sort of big omnibus containers for many of the things we want to do soon, are Project Valhalla and Project Panama. I'll say more about them, and so will Brian, and so will Carl Taylor. But for now, I want to go through some of the component initiatives inside Valhalla and Panama. All right, time for values, and time for a time check. I'm 20 minutes into my talk. Good. What's a value? One thing that I've noticed about computer science is we throw terms around, and they're often very good terms. They're very poetic, very rich, very resonant. Sometimes they go back 5,000 years of continuous cultural history. We pick good words often, and we never define them. People would say, oh, that's a closure. Oh, that's a continuation. I can find places in the literature where the word pops up and nobody's defined it. It seems poetically right to talk about, well, that's a closure of code over some local values. Oh yeah, I see the data structure, and I see what you mean. Yeah, that is kind of like a closure. No, it's not a cleany closure, but it's a new Lisp computer science closure. Okay, got it. Now we do closures. That's the way terms pop up in our industry sometimes, and value is one of those terms. So I'm going to just sort of make my own definitional rampage here by starting 5,000 or 6,000 years ago with Proto-Indo-European. The word value comes from a root common to many languages, including Sanskrit and Latin and Greek, that means strength. And the way, after a millennium or 5, that word started to be used in a commercial sense, referring to price, referring to what the thing is intrinsically worth. So the value, a thing is of value if you give money for it, or if you give a sheep for it, or whatever the medium of exchange is. One reason people say this is an ancient word that people in pre-literate societies spoke, and they said something like wall. No Indo-European is written down, as probably you know, but there's all these cognates, and so I listed them because it's fun to look at them and say, yeah, those do kind of look like related terms almost. As long as we're talking about millennia ago, here's some old technology, previous generation. This is how writing, according to one theory, a very plausible theory, came about. It started with people needing to record value, record commerce, commercial transactions, contracts, things like that, from one city in Mesopotamia to another, leading a bunch of sheep from one market to another. How many sheep do I owe you? Well, we're making a contract. We're going to put it inside an object that is going to represent, using tokens, the number of sheep that I owe you. And I'm going to write on the outside of this clay-fired object something about what's inside it too, just to make double sure, and I'll put my signature on it. And then I'll clay-fire it so that it's got a secure wrapper, and it's not cryptographically secure, but unless you sit on it, it's going to make its way to the next city over, so you'll be okay. Turns out that this technology is pretty buzzword compliant by modern terms, as you can see. It's got a sub-centimeter fabrication process, very advanced. Those little tokens are about like that. You know, it takes a little bit of effort to build them, and they're very durable. Probably a low noise rate, unless you drop the thing in the Euphrates River. And I think it's so cool that somebody ought to write up a patent disclosure for it. So I gave the first phrase there at the bottom of the diagram. Yeah. Yeah, there's prior art. Yeah. But maybe somebody's filed a continuing whatever those continuing resolution patents are. You know, one every 50 years, and only take about 100 of them. So this is how it used to be, but the fun part is people realized pretty quickly that the tokens and the spherical wallets could be improved, that you could flatten out the spherical wallets and just put impressions or marks or stamps of the tokens on the spherical wallets. In fact, you flatten, hey, we're going to talk about flattened data later on. This is the original flat data. You take a piece of clay and you go stamp, 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 and no more little tokens. Much more efficient. And so this, here's a selection of stamped and or painted and or gouged writing systems from various times. And you can see some of them are quite artistic, and others are very businesslike, like the Sumerians. Once they got into the cuneiform, it was very businesslike. That top left picture is a later evolution of what you do with a reed stylus and a flat piece of wet clay. You use the stylus to make these cuneiform writings, which get quite beautiful, and then you fire it, and then it's your permanent record. It's write once memory. But clay is not the best medium. Paper's better. So once people got the idea that you could write these things down, and that it was good to be able to quickly write them down and not have to make a whole art show out of it like the Egyptians would do in the previous slide. That Egyptian hieroglyph thing is beautiful to look at, but it took a while to write. So it's a long latency for recording data that way. If you have a scribe with a little quill pen and some cheap ink on papyrus, then it's a very much faster bandwidth to record stuff, to put your tokens down. So paper's better. And then, of course, here's some stamps, which we're skipping over the entire history of movable type and going into the near present with government stamps, which are, again, they contain values, don't they? The Greek there is one of Plato's dialogues. So you can put some pretty cool stuff using these tokens. So, all right, let's get to computers. What does it mean for us to have a value? Well, I would argue that a value, and in line with these other uses and origins of values and signals, is an indication of something concrete, something closed-ended. It's not a vague cry. It's a choice of one of 26 letters. They can be, here's the most important part. Here's where I distinguish values from objects. They can be created or recorded. They record a thought. They can be recorded and copied at negligible cost. This is where for us, the GC turns out to be a hedge against everything being a value, because it is not negligible to record an int inside of a Java-lang integer. It's cheap, but not negligible, as we've found. So a value is something that is recordable easily, quickly, without thinking. It's not a clay-fired tablet. It's not a memory-allocated, managed storage block. It's a quick stroke of the pen. In the setting of the JVM, however, because we have a strong commitment to manage pointers, a value can also be a pre-existing pointer. In other words, if I have a pointer to something I've already paid the cost of creating, then I can copy that pointer very cheaply all over the place. So that's a great trick to use. We don't want to not use that trick. So according to the wonderful paper in mid-20th century by Claude Shannon, where he sort of proposed using the word binary digit or bit as the unit of information, and he talked about the entropy of human language and things like that, all values boil down to bits. So now we're on comfortable territory, right? We all know how many bits are in various pieces of computer memory, and that's something we're used to thinking about. It turns out to be fundamental. If you have decided that you're going to pick very crisply one out of a set of symbols, and that's something the Sumerians did way back when, they're going to distinguish a sheep from a horse, and it gets down to bits, as the 20th century thinkers found at the dawn of computer science. But in the JVM, there is one special kind of bits, which is a pointer. A managed pointer is an opaque collection of an unknown number of bits that cannot be interconverted with other bits. So we have bits and oops is what they're called in Hotspot. Okay, now back to artifacts. Here's what you can do to represent a value using an object. You can put some stuff inside a hollow sphere and wrap it around, and that's the moral equivalent of going to your T-Lab and allocating some storage and stamping a header and then putting your payload into it. You can do that. There's a cost to it. Or immutable objects like coins are a somewhat more well-behaved way to do the same thing. You stamp out a coin, and no one's going to change the obverse of the coin to have a new image on it. And so it's something you can hand out and know that it's going to mean the same thing when it gets to some other recipient. So that's like an immutable object, but it's still costly to produce. And in fact, coins are made of precious metals so that they are hard to produce. Values are better for many purposes because you just have here's a 16-bit code point. Oh, that's a smiley face. I've got a whole range of ways, including pen and paper or xerographic printers, to just put that down somewhere and I'm done. Cheapest way to transmit information. So as you've already guessed, I would call primitives and even some uses of pointers to be values. So we're already done, aren't we? No. The problem with the JVM is composing values. So what we want is composites that act like values, that act like ints, but that do not have to have the overhead of storage in the heap, at least not always. Of course, we want ints in the heap as well, but we don't always want our ints in the heap. That's the thing. Another thing we want to address with composites is the Java memory model. We want them to be well behaved with respect to concurrent changes. And the simple answer is let's get rid of object identity, which concretely speaking means let's get rid of pointers. Pointers are well hidden from most daily uses or users of the JVM, but we all know they're there. And they show up in lots of ways, even if you don't look under the covers of the VM. So what happens if we throw away pointers, if we get rid of pointers? Because I would argue that's the main thing that's keeping us from being able to have cheap to create and copy values. Well, if you get rid of pointers, you can't do locking. There's no object header to do locking on. There's no identity comparison, no identity hash code. There's only structural hash code. You still have comparison. It's just not comparison of identity because there's no identity anymore. Cloning doesn't make sense. How do you clone 42? You don't. You don't need to. Null is an odd thing. There's no longer null values, so you need something more like optional. and there's no side effects. And one thing that's not so obvious is that it's very hard to talk about subclassing and pointer-based polymorphism if there's no pointer. So the object extension trick doesn't work with values, near as I can tell. All right. This is a concept of a pointer irrelevant or value-based class, which is actually hidden in the documentation of JDK 8. Some classes are documented in nice readable language that they are value-based. And that means you should not do any of these pointery things with them because you might get uncertain results. We don't enforce that in JDK 8. We just say, you should realize that some classes are value-based. We're going to double down on that now. We're going to point out a design pattern here with, here's a two-component point, fully immutable, not subclassable. Doesn't matter whether the fields are public or private. Has a constructor, can't change the value, the thing outside of the constructor. It acts like a value. In fact, this is a value-based class. This is a class that you would be wrong to try to synchronize on. So does that give us value types? Wouldn't that be nice? Wouldn't it be cool if we could just have a design pattern and then all the optimizations that we get from ints would come from these objects too, and you could return a pair of integer values via a point as a box, and the VM and everybody else would just say, oh yeah, he's doing that value class thing again. Of course we don't need the pointer. We'll put the 2 points in 2 registers and return it or pass it as arguments, or do all the compact things that you do in other languages with compact structural values. Problem with that is there's no way to reliably obtain it. You make one mistake and the optimization goes away. Or the VM makes a mistake and the optimization goes away, and everybody's frustrated. So what we need are new types. Fundamental new guarantees need fundamental new types, and that's where we've come to in our long discussions about this. What does it look like? Well, it could be quite simple. Just add a little markup to the previous class, and it's a value type. What does that mean? It means that the JVM has a different set of performance guarantees and model on it. And in particular, if you try to do any of the pointer things by accident, like synchronize on it, you'll get a diagnostic that will tell you you did bad. Can value types have methods? Well, sure. Why not? A method is a piece of shared code. Maybe internally this thing doesn't have a pointer to the point, like a this pointer, but it makes sense at the language level to talk about this. It means you select the X that pertains to this, and it's probably copied into the method instead of passed by reference, although that's a VM detail. Should it have equals and two-string methods? Well, yeah, we like that stuff. Even int has equals and two-string methods, although they're spelled funny. Our mantra here is codes like a class works like an int. We want to be able to use all the class definition machinery that the VM supplies and the Java language. And yet, when you have created that class and you've made an instance of it, instance in quotes, right? There's no pointer, so it's not really an instance, is it? Well, it should just work like an int. That means it's in a register somewhere, or if it needs it, it's in 2 or 4 or 10 registers. It's not necessarily in the heap. Here's some examples of coding with it. Here's another syntaxy speculation. How do you call the constructor? Well, you might say new point, but that seems awfully heap-like, so I'll just put a syntactic placeholder in there. So here's an example of working with points. These statics could be in any class. What do you get? Well, one thing that you need along with these values is for each value type, you need a customized box type that goes with it. So there's this sort of evil twin thing going on. The normal form of a value is broken out into registers or in laid out in somebody else's field or an array. But it can, if necessary, you can box it up and treat it as an integer. But this is seen as a slightly unusual step, kind of like auto-boxing an int into an integer. In fact, exactly like that. The methods, one very important thing about values is that remember the important hallmark of a value is that it's cheap to create and copy. So these things, these pointer-free values are inexpensive to create. It just involves materializing some values into some registers. And for copying, it means moving those registers into or out of memory. There's a certain problem with tearing, which I don't have time to get into, but we have some solutions for that too. The essential insight is that we want these things to be securable when they need to be. Fields can be defined, access permissions work, and via the boxes, we can have all the nice, comfortable object-flavored features we want. In other words, if I box my point into a point box, then I have Java-lang object, I have reflection, I can do all the object-flavored things with it. It even makes sense to define interface methods on values through this channel. Now, you're probably squirming with the double underscores. That's intentional. It's not a JVM thing to define language syntax. And Brian does that by fiat, and everybody agrees with what he says. So we just do whatever language things Brian says. Ha. Yeah, I'm too much of a coward to get into language design, so I've just put the placeholder syntaxes in. All right. There's a lot more details to say about values. I'm not going to give you very many more. The important thing is that it codes like a class and works like an int. That will answer most of your questions about how values should work. Moving on, use cases for values. They're the kinds of use cases you think of. One that, like numbers. One that's very interesting to me that maybe is not quite so obvious is when you have foreign data subject to foreign rules and maybe internally unsafe operations to get to that foreign data. I'm talking about C or maybe some other data schema that's not part of the Java heap. How do you encapsulate access out to that data on the side somewhere? The answer, I believe, the best answer, is to use a value type. Use the classic idea of a foreign function pointer from Lisp. A foreign function pointer consists of some metadata telling what's being pointed at, a raw machine address to point to it, and maybe a little bit more bookkeeping information. But it's basically a tuple of between 2 and 4 components. Sounds like a value type. And if you make it a tuple of between 2 and 4 components, you can copy it in and out of container types without too much more overhead than if you were manipulating simple references. And the GC churn is much more controllable because every time you create a new value, you're not creating a new heap node. You're just assembling registers and putting them down into a wide field somewhere. So I think one of the compelling use cases for value types will be native interconnect for safe pointers in particular, but other uses too. Briefly about arrays. How do we do arrays? Well, surely we just need one more array type and then we're done, right? Everyone knows Java arrays are wrong for many uses, so obviously they forgot to put the right arrays in the design, so let's get the right arrays in, and then we'll have the wrong ones and the right ones, 2 array types, and we're done. And of course, it doesn't work that way. And the fundamental reason is there are many degrees of freedom in the design of arrays, and I've written about 8 of them here. And you can probably think of more. Arrays are really complicated. Maybe individually they're simple, but as a total category, perhaps, there's no categorical array, at least not for the hardware and the languages that we're looking at. So, what do you do? Well, it's like being in the restaurant with a 20-page menu. It takes forever to order your lunch. The better way for a restaurant like that would be to supply the user, the customer, with a nice list of fresh, healthy ingredients and tell them to choose an omelet based on any 3 of those ingredients. And I think that works for array types also. the key architectural task is to find out what are the fresh, healthy ingredients for arrays, the tricks that we want arrays to do, and then supply them in the JVM in a way that library designers can mix and match them according to the needs of their ultimate customers. This is driven both by the present JVM and also by the Java language as it stands now and how it's likely to evolve, but also about it's driven by the nature of the hardware underlying it. So what we need is a kitchen with the right recipes in it. The basic ingredients include, I would argue, and this is in a JEP, which we're working on, the classic arrays, some internal chunking nodes, including perhaps some new ones like low-arity B-tree type nodes, the ability to make a blocked array. Well, what a concept, an array that's locally flat but has manageable blocks, so you don't need to copy the whole thing when you change one thing. Some concurrency strategies, which current arrays fall down worst in. There's no such thing as a frozen array, or you can lock an array, but it doesn't mean anything. And then beyond that, some APIs and default methods and classes that we can build good stuff on top of, and maybe a little syntax if absolutely necessary. Arrays, by the way, should be large if necessary, should have 64-bit indexes, but they should not be large contiguous blocks. The natural size for flatness, we'll get into this later, is more tied to the cache line, not to the address space. I'm going to skip the API notes. They can be found in the JEP that is in process, but the operations we want to supply on arrays can be generic and are unsurprising. APL has done a beautiful job of exploring that space for eons. I'm going to skip this part about JVM support for arrays so that I don't completely nuke Brian's time for talking about the stuff he wants to. Just a very few words about native interconnect, and this is under the heading of Project Panama. Values are under the heading of Project Valhalla. What we want to supply is what Charlie was asking for, a way to quickly get to foreign code and data structures from within the JVM without a lot of overhead and difficulty. And I would say we also want wrapper interposition mechanisms based on interfaces so that we can push or pop adapters onto native capabilities without changing types all over the place. Layouts are important too, not just foreign functions, but foreign layouts. And to that end, we're working we have a prototype that works in terms of a calculus of metadata-driven layout descriptors, which then turn into these foreign pointers I described earlier. And it seems to be a powerful way to work as long as it all optimizes. And value types will make it robustly optimized. Right now, we're just working with boxes. As a bonus, not just C will be supported by such an architecture, but any layout that is application or architecture specific. I see that Facebook smile over there. Yeah, just thrift. I'll just use the word thrift. There are synergies between the initiatives, and there are too many to point out. But one of the good sort of signs of virtuosity here is that what we're planning to do feeds off, the different components appear to feed off of each other. Makes it hard to phase them in one at a time, but once they're all in, they will mutually improve each other. I want to give a shout out to those customers who are desperately struggling with GCing and want off-heap data for that reason. Yes, we hear you. This is something that has to be done, supported well with native data. Lots more to say. No time to say it today, but it's still out there. I particularly want to figure out someday how to do coroutines right. I think GPUs are demanding that we get something lighter weight than a thread as a unit of sequential computation. So I think that's enough for me right now. It's plenty to think about, isn't it? Brian's got even more. And I think I think it's time for you to come up, Brian.
So, John has been talking a lot about how we want to evolve the JVM, and these are sort of foundational decisions that have long-reaching implications. If you talk to most users, they don't really make a differentiation between the Java language and the Java VM. Obviously, everybody in this room, deeply understands, the distinction. But most people, who program in Java, they say, well, why don't you just add this to Java? Add unsigned into Java. And they don't really have much of an idea that whether they're talking about language evolution, VM evolution, what the effect of one on the other is, whether this is even a library thing versus a language thing. So it's kind of good, actually, to hold on to that naivete about where the boundaries are, because when someone says, why don't you make this improvement, it offers you a reasonable opportunity to ask, well, at what level is the right level to make this improvement? So when presented with an arbitrary language feature, we have a lot of choices in front of us. Historically, our approach for language features has been to do everything in the front-end compiler. So, Java-C generates different bytecode, based on what was asked for. But most features that we've implemented since the beginning of Java have been implemented entirely in the front-end compiler. So, generics are a compiler fiction, checked exceptions are a compiler fiction, auto-boxing is simply a feature provided by the compiler, and then it just, for as far as the VM knows, it's just calling these methods like value of and things like that. And that's usually the approach we've taken, and that's usually the sensible approach. At the other end of the spectrum, we could do something different. We could say, for every new feature we're going to add to Java, we're going to add new bytecodes. I mean, obviously, we'll run out of bytecodes, but we can add new bytecodes. And that's a possibility. It's often a silly choice, but it's something that we should realize is one of the choices that we have. And in fact, bytecodes are not the only thing that we can add to the VM to get more functionality at it. We can add new constant types. We can add new class file attributes that have semantics. We can add privileged runtime like invoke dynamic. We can add features into unsafe, which has been largely a dumping ground for things we'd like to be intrinsified but don't yet quite know how to spell properly, so we dump it in the unsafe bucket. And then the front-end compiler is just like a dumb assembler for the VM features, and that's an entirely valid way to do it as well. It's may not necessarily be the right way all the time, but sometimes, for some problems, the right answer is somewhere in the middle. That there's some division of we need certain basic features from the VM, and then we can build on top of those features in the front-end compiler to make them work. And ideally, we'd like to select that division of labor in a sensible and non-random way. And of course, the difficult part is finding that balance. And so, there's this tension between you would like for the basic language model and the basic VM model to be largely in sync with each other. For those of you who are maintaining languages that are very different from the Java language and have impedance mismatches with the JVM, there's no end of pain, right? And we understand that's a very painful thing. And so you would like, even if the language is adding things that the VM doesn't support, like the VM has unchecked exceptions, Java language has checked exceptions. There isn't really an impedance mismatch here, right? So, but there's certain, if you have a language whose numeric types don't fit neatly into Java's 32-bit and 64-bit integers, you're definitely in a world of pain. So, on one hand, we'd like to minimize the conceptual gap between the language and the VM. On the other hand, just dumping the language's problems into the VM is not a good idea either, right? So this is the tension that we find ourselves in, and this is a very tricky balancing act, right? We don't want to simply export the language's problems on the VM, and while Oracle is in sort of a privileged position where the language issues that we run into, we have the option of solving them in the VM, whereas other languages don't necessarily have that option. We don't want to pull that lever unless it benefits everybody. So, the way to win is to find the VM improvements that are language agnostic, that benefit multiple languages, not just the Java language, and then put them out there where people could use them or not. So a good example of one of the things we did in Java 8 was the way we did Lambda conversion in Java. We put some runtime in the language runtime, Java lang invoke, for I've got a method handle and an interface I want to adapt to it, and you can use this as an invoke dynamic bootstrap to make a Lambda, and there's obviously, there's a pipeline of optimization that we intend to apply to make that more efficient, and other languages that have closures can choose to use this mechanism, and if they do, they'll benefit from that future work, and if they don't use it, that's fine. It's just a tool in the toolbox. So, rather than build something just for Java, we partitioned it into here's some general tools that are useful to multiple languages, and here's how Java's going to use it, and if other languages want to use it in the same way. A good example of what we're not going to do, and I know a lot of people in this room are a little bit nervous that we might be getting this idea, is something like, let's take Java's generic type system with wildcards and all that, and let's just push that whole thing into the VM. Right? How many people think that's a great idea? Right, it's not a great idea. It's a bad idea. The reason it's a bad idea is Java's type system is Java's type system. It is not necessarily the right type system for Scala or JavaScript or JRuby or really any other language besides Java. So it would be silly to take this, take these type notions that are very tightly tied to the Java language and burden every other JVM language with them. Right? So it takes a fair amount of taste and judgment to figure out what the right language agnostic building blocks are. So let me talk a little bit about the language initiatives that we've got going, and I'm very quickly going to turn this back around to JVM stuff. So, this is it's important to sort of look at why we're doing these things, because this is the value that we're that we want to offer to our users. The big language features that we're looking at right now are specialized generics, which is generics over primitives and also over value types. So right now, if you want a list of integers, you can make a list of integer, but you can't make a list of int. And that kind of stinks, because we're putting users in a position where they have to make a choice between the abstraction offered by a parametric polymorphism and the performance offered by primitives. And you can have one or the other, but not both. And that's kind of a lousy choice to give to people, so we don't want to put them in the position where they have to make that choice. Our approach for that is going to be based on dynamic adaptation of classes and also of generic methods. So you can write a generic class. The Java compiler will produce a class file very much like it does today that deals with objects. And then if you want array list of int, a transformation process will spring into action and convert the class to work with ints. And in the design work for that, this motivates several general purpose VM features that we're considering as a result, not because we can't implement specialization without it, but because it seems a good factoring of the problem where it offers benefit not just to the Java language, but to other languages as well. John talked about value types in the VM. We clearly would like to expose value types in the Java language. One of the most frequently requested features for Java, now that we finally did lambdas, is tuples. Where are my tuples? And value classes are a very, very handy way to implement tuples. One of the reasons we've been reluctant to just implement library-based tuples in the Java language is because of the boxing overhead. Again, forcing users to choose between a nice abstract representation of something and something that actually works quickly. And the last one that I'm going to talk about briefly, but mostly as an intro to the talk that follows, is a better and more general way of accessing data no matter where it comes from, whether it be on heap, off heap, and also abstracting over all of the different fencing modes that modern hardware can offer us. So, okay, let's start with specialization. Why are we doing this? Well, we can answer that question by looking at why are we doing value types at all? So what is better about a value type than an object? They're both aggregates. They both can have methods and fields, and some of those fields might be private or public, whatever. So why would we build something that's so similar to something we already have? And the answer is, well, classes give us the expressiveness we want, but not necessarily the performance we want. And the performance pain of expressing value-like things using objects comes from a number of places. One is memory footprint. Objects have to have an object header. So representing a 4-byte integer with 8 bytes of object header seems like a fairly high overhead. In addition, if you have, say, an array of boxed integers and you want to add them up, every time, before every addition, you have to do a pointer dereference. Probably means you're going to do a cache miss. And so what was adding up a bunch of numbers turns into a storm of cache misses, and it's likely that the performance of that is going to be memory bandwidth bound rather than CPU bound. Objects have complex semantics because of their identity. Their VMs have to reason about aliasing and things like that when they're trying to do optimization. And making a new object involves allocation and garbage collection. And that is sort of an accidental cost if all you want to do is copy a number. So the key theme of why we're looking at these features is we want to take away the places where users have to agonize between doing it the right way and the fast way, because we know they're always going to pick wrong. So, if you have a choice of, well, I can do things in the nice abstract type-safe way, or I can cram 2 ints into a long with some bit twiddling, and that'll be a lot faster. Well, maybe it'll be faster. Maybe you actually need that performance. Maybe you don't. But, oh, the poor guy who has to read that code next is in trouble. And as George said earlier, we want code to be easy to read. We want people to look at Java code and say, I know exactly what that does. Because when people look at code and think they know what it does and don't, that's where bugs come from. So we don't want to put people in a situation where they have to choose between abstraction and performance. So that's why we're doing value types. That's also exactly why we're doing specialization. We don't want people to say, well, I can use list for shoes, but not for ints. For ints, I have to use something else, or I have to cram them into an array, which now they're going to be mutable, and I have to ask people really nicely, I'm going to give you this array, but please don't scribble on it. We don't want to put people in that choice. So, all the reasons for value types apply for generics over values as well, right? If you have an array list of integers, it has all of the same defects as boxed integers. You have boxing, you have footprint, you have a loss of locality. When you're iterating over it, you have to worry about aliasing. That's a mess. Really, what the user wants is array list of int. And they'd like it to be backed by a real array of ints, not an array of boxed integers. So this was one of those things where, the glass is, 98% full or 2% empty, and we like to focus on the 2% empty, right? When we did generics, we made this conscious choice of, well, we can generify over all the reference types, and there's a lot of those. We can't generify over the primitive types, but there's only 8 of those, and eight of these, infinitely many of these, it's almost perfect, right? So using the same calculus, once we have value types, and there's Aleph null many reference types, and Aleph null many value types, plus 8 primitives, well, now there's more things that we couldn't generify over. Generics are now, at best, only half good, right? And we don't like to be in the business of providing half solutions, so obviously we have to do something. Okay, I make a joke of this, but today's problems come from yesterday's solutions. It seemed good enough, 10 years ago to say, yeah, generics are good for polymorphism over reference types, and we're going to live without polymorphism over values. And in those intervening 10 years, the pain of living with that restriction has proved more burdensome than we maybe optimistically hoped it was 10 years ago. Okay, so how does it work? Imagine we have a simple class, box of T, okay, and notice there's some syntax here that says this is not just an ordinary generic, this is a generic that can range over any type. Again, we could bike shed on the syntax endlessly, and no matter what I say, we will, but let's not do that right now. So you have a class, here has a field of type T, has, a constructor that lets you stuff a T in, and a getter that lets you get it out. So what do we do when we compile this now? Well, we erase it, right? And so we replace all those T's with objects, and then anybody who invokes a method on a box of T, you invoke the get method, the compiler inserts a cast on the way out. So it returns object, and then you cast it to whatever you think it's a box of, maybe box of string or box of shoe or whatever. Now, if we wanted to specialize box event, we would need to have different signatures. The get method wouldn't return an object, it would return an int if this were a box event. And this is already problematic for many of the reasons that Attila mentioned yesterday in his talk about how JVM signatures and bytecodes are very strongly typed. And if you want to describe a family of things that may range over different types, you start to feel the pinch of that. So what we conclude is, it was a clever trick to cheat by using one class to describe, all instantiations of box of T where T is a reference. This trick doesn't scale very nicely to non-reference types, and we're going to need a different trick for addressing that. So we have two choices, and we really only have one choice. One choice would be try to unify objects and references. If you saw Paul Phillips' talk last year at this event, he talked about some of the pain that the Scala folks have had trying to make that unification while retaining compatibility. Or we could just admit reality. Just as we have, there are reference types and primitive types. When you generify over types, you're going to have generics over primitives and generics over references, and that's kind of the reality. So let's look at how this might work. So let's say we have our box of T class, and we want to specialize it for T equals int. We have to mangle some things, but we don't just mangle the signatures, right? So here's the bytecode, from that class that I just put up, and we have to do quite a bit of mangling. We have to mangle not only the signatures, but also the bytecodes, and we also have likely to mangle the name of the class, because whatever the class representing box of int is, and it doesn't matter how it's spelled, it doesn't extend box. Because the signatures in box and the field, especially the field signatures in box, aren't a match for the signatures in box of int. So just as integer and int aren't related in the type system, box of integer and box of int aren't going to be related in the type system either. So there's a couple of different kind of manglings that that we've shown here. One is we've mangled the name of the class, and this is one particular way to spell the mangling for box of T with int, but we're not going to impart any semantics to that. We have to mangle the signatures, so the argument type of the constructor changed, the return type of the get method changed, the field descriptor for the field changed. And then some of the bytecodes change too. What were A loads and A returns and A stores and AA loads and things like that, some of them become I loads and I returns, et cetera. And if I turned them into D loads or L loads, I might also have to renumber the local variable table, but that's my own personal world of pain I won't burden you with. So there's a lot we have to do, but this is a mechanizable transform. This is, we don't have to go write a new class for box of int. Sufficiently patient, entity like a computer can transform mechanically the box of T into box of int. Okay, so how might we do this in real life while maintaining compatibility and not pulling the rug out from everybody? Well, the class file format allows us to put extra metadata into a class file that people who don't understand it are free to ignore it. So that's basically the trick. So there are a number of places in the class file that is the result of compiling box.c with the Java compiler where it's where the type object is going to appear. And sometimes object means the user typed object. And sometimes object means, well, I had this type variable whose erasure, variable T, whose erasure was object, so I'm going to write object in the class file. So you see I've noted in red a couple of places where something says object or something says A load, and I've put little red asterisks to say, yes, this thing that I'm calling object now, this originally was a T. So if you don't know about specialization, just ignore the little asterisks, and it's a class file just like any other you've seen before, and you just load it and you're happy. But if you do understand specialization, I'm giving you some extra data that says this thing that says object here really is a T. And this A load over here is moving around something of type T. So if you swap T out from under me and turn it into int, you might have to adjust this bytecode as well. Okay, so we've got a prototype of this in Project Valhalla where there are 2 new bytecode attributes that basically describe these asterisks, and If you ignore those attributes, which everything except the specializer does, it's the same class file you've seen in the past. And if you act on those attributes, then you can reason about the where some of those choices of object came from. So this is kind of a clever pun that we're using the class file for, where the same class file serves double duty. One is it's the same class file that we've always used. It represents an erased version of a generic class that you can load and use without any modification. And in fact, the bytecode we generate, other than these extra attributes, is no different than what we generated before. But also, we can use this class file as a template. We can use that template to create transformed versions of this class. So when we want to stamp out box of int or box of long or box of some value type, we can mechanically post-process the bytecode and produce the the desired specialized version. So that solves part of the problem, but there's another interesting part of the problem, which is, let's say I have in my source code, I have a variable of type box of t, or I have a class that extends box of t. How do I write that in the class file? I don't know what the name of that class is going to be. I mean, you saw it got mangled to box $t equals int, but it would be terrible if we said, yes, that's what you actually have to put in the class file, is this mangled name in order to reference this type. So, since we don't want to impart the semantics to a naming convention, because that's gross and hacky and will almost certainly come back to bite us, we need some way of writing box of t in the class file. Well, what does box of int mean? Really what it means is take the class box and apply a specialization transform to it with a parameter t equals int. So we want to describe in the bytecode the result of applying this transform to a set of classes with some parameters. How do we encode that in the class file? Well, some of you probably know where I'm going, which is that sounds an awful lot like an invoke dynamic call site, right? You have an opaque behavior handle that says, how am I going to do the linking? Which is your transformation function, like the specialization transform. And then you have a bunch of static arguments, which are just constants in the bytecode, of what am I going to apply this thing to. So those arguments would include box and int and maybe other direction about how to do that. And together, this constitutes a structural way of describing a class. I'm not saying the class called X, which will be loaded from the class loader by asking the class loader for the thing named X, and it's going to hand you a bag of bytecodes. I'm saying here's a process for describing a class, for deriving a class X from some other data using a transformation process and potentially some other classes. And this is a really powerful tool. The working title for this is class dynamic. And it's a way of structurally describing, here's the class that I want. Run this this class generation process, which might generate classes on directly, or might transform other classes, and give me the result of that. And if two people ask for, I want the specializer transform with parameters box and int, and two different classes ask for the same thing, they're going to get the same class, because these structural descriptions are compared structurally. They're the same class if their bootstrap is the same and their arguments are the same. So our strawman approach for implementing this is, we're going to create a new constant pool type. Maybe this is actually how it's going to work. Maybe it's not. This is all, hand wavy. But just as we have class constants, there could be a dynamic class constant. And the structure of a dynamic class constant will look basically just like an invoke dynamic call site. And all the places in a class file where you can reference a class, my super types, the type of a field, the types that appear in method signatures, the types that appear in stack map tables, things like that, you could use a dynamic class as well as a nominal class. So for purposes of writing it down in a talk like this, I'm just going to use this notation, class dynamic, open braces, the name of the bootstrap, and the arguments, but that's just a notational convenience. And so the way we would write list of int is class dynamic, the bootstrap is the Java specializer, about which the VM knows nothing, The Java compiler may know something about it because it's part of the Java language runtime, but the VM doesn't have to know anything about what it does other than, given some arguments, it gives me back a class. And then the arguments to that bootstrap are list and int. Pretty straightforward. So the VM is, there's sort of this conspiracy between the compiler and the bootstrap, right? The compiler has generated code that says, I want the class that is a result of running this bootstrap, and presumably the compiler knows what the bootstrap's going to do. It knows something about the semantics of it. The VM is an unwitting participant in this. The conspiracy is entirely between the language compiler and the language runtime, and the VM is just the mechanism for doing the plumbing, which is as it should be. The VM should not be involved in the semantics of these things. Okay, this all sounds like a lot of abstraction because it's cool, which it is cool. But you don't have to think about this for more than a few minutes before you realize that there's a zillion problems you can solve with this. Basically, any mechanized class transform, which very often we expand by hand, like when we write wrappers like synchronized wrappers and things like that, or the adapter classes that JRuby emits, for making calls to the Ruby runtime that do all kinds of argument adaptation. These could all be mechanistically described and generated on the fly and described by class dynamic. So specialization is one possible transform. Dynamic proxy of I generates something that implements I and whose methods do something that is can be mechanistically generated. Synchronized wrappers, forwarding proxies, the kind of classes generated by reflection, to bypass the reflective path when you decide that you've called this thing reflectively enough times and it generates an unreflector class. Tuples and structural function types are an ideal application of this, and especially if you combine this class dynamic method generation with being able to generate a value type, some really cool things come out of that. So like I said, tuples and arrow types fall out of this almost trivially. So a lot of the code generation that we're either doing manually or with IDEs or with code generation tools, we can move to runtime and describe in the class file the recipe from which something is generated rather than it just being an opaque class. Okay, so that's pretty cool. How hard is that, right? That's not too hard. Well, there's all kinds of challenges along the way. Java also supports generic methods. For specializing generic classes, we have to specialize generic methods as well. So here's an example of a generic method. If the compiler infers int for t, I'm going to need a different implementation of identity int from identity object. And this has all the same challenges of specializing classes, and then some extra bonus challenges as well, because while it's really easy to make new classes, it's not so easy to wedge new methods into an existing class. And well, maybe we could cheat by statically generating the 8 varieties we want, but that both sucks and would fall apart terribly when we got to value types, so we wouldn't do that. So we need a little bit of help here to hook into nominal method linkage in order to be able to support generic methods. And there's a couple of ways we can do this, and this is, now we're generally entering the speculation territory, so, definitely don't make product purchase decisions based on what I'm going to tell you here. But this is not new ground. A lot of languages have covered this ground before. The notion of a method missing handler is a pretty well understood concept in a lot of other languages, and that is one tool by which we could solve this problem, where if we had a method missing handler associated with the class that would consume a signature and would cough up a method handle when asked, right before we were about to throw no such method exception, we could consult the method missing handler, see if it can provide us with method handle, and then add that into the class. And how that interacts with reflection, well, who knows? But that's one possibility. Another possibility is, well, we already have a tool that hooks into method linkage, invoke dynamic. So we could invoke generic methods just with invoke dynamic, which would be simpler and less general, but that's also a possibility. Okay, so a few challenges. Supposing I write this generic class array list of any t. Well, now it's great. T can range over not only reference types, but primitive types. But the generic implementation might not actually be ideal for certain specific types. Like, I can think of a much better way to write array list of Boolean than having an array of Booleans. I could pack them into, into longs instead and use less memory. So there are times when this genericity is nice and abstract and flexible, but you might want to be able to override it. So you might want to be able to override the specialization of a particular class or the specialization of a particular method for a particular combination of type arguments, or a specific instantiation of a generic method. Or maybe I'd like the list of int to have more methods than list of t, because list of int could have a sum method. And wouldn't it be nice to just say list.sum, and that's statically type checkable. List of int can have more members than the list of question extends object. And we spent a fair amount of time talking to folks who worked in .NET, where .NET is a little bit ahead of us on some of these things. Their generics are reified and can range over both reference and value types. And there were some very common pain points that emerged from talking to these developers of, it's too generic. I can't do something different for values versus references. I can't do something different for int versus the rest of them. And so these are real limitations. And just as we talked about the not being able to generify over these 8 classes. Well, that's only 8 out of infinitely many. How bad is that? We were able to learn from some of the mistakes, or the optimism that the .NET folks made when designing this out. So these are some challenges, and there's actually some more challenges that show up when you try to actually generify the Java class libraries. Like, our generic classes are full of assumptions like, well, I can always assign a t to an object, or I can always assign a t array to an object array, and obviously you can't do that if t might not be an object. But then how do you write array list? Array list has to have some way of saying, I need a new array of t. You can't assume null as a valid value of t. Well, that's obvious, except what about map.get? What does map.get return if you don't find the key in the map? Oops. Or things that were acceptable overloads, like remove of t against remove of int in list. That's fine if t can never take on the int as a value, but you try to generify that, and like not being able to generify our existing collections. Well, we'd look kind of silly, wouldn't we? So we need a way of solving these things, and we actually have a plan for that, and it's outlined in the public document that's been published on the Valhalla list. I won't go into all the details, but the basic idea is all of these problems are solvable with a notion we call conditional methods. So these are methods that appear or override only in certain instantiations. So for example, and again, straw man syntax, don't bike shed on this. You can mark a method as, this method is only relevant to a certain family of instantiations. So we have a class ArrayList. It can take on any value for t. And if t is int, it also has a sum method. If t is long, it has a sum method that returns long. How would this work? Well, this is a very straightforward generalization of what I was just describing, where you have the class file is acting both as, here's the erased version of ArrayList of t, and here's the template of ArrayList of any t that you're going to use to specialize. Methods that aren't applicable to the erased version would get ignored during class loading, but they would get acted on by the specializer. So the specializer would look at them and say, oh, I'm specializing for t equals n, so I have to copy this method into the output. I'm not specializing for t equals long, so I don't have to copy this method into the output, etc. And we think that the set of conditionals, some primitive or value type, any reference type, or any value type is enough. We're going to experiment with that and see where that takes us. Okay. I'm going to talk a few minutes again about value types, just in terms of how they would be surfaced in the surface language. John talked a lot about how they would work in the VM. So we have the heterogeneous aggregates that Java gives us, classes, are great, except that they come with identity, which we don't want, right? So value types are heterogeneous aggregates like classes, but without identity. But we can still borrow most of the concepts from classes, that we're familiar with, methods, fields, access control, et cetera, and we can still declare them like classes just with some restrictions. So there are restrictions on inheritance, there are restrictions on mutation, there are restrictions on cyclic containment. If you have a value type node, it can't contain a node because since its fields will get flattened into it, that would make it an infinitely large thing, and it can't do that indirectly either, right? So there are a few restrictions that we would need to apply, but the goal would be it would not look too unfamiliar to to ordinary Java developers. So you have some token that says this class is a value class, and there are some things you can't do. The compiler will tell you can't do that if you've done it wrong, but it should be familiar, and it would be perfect if the VM could just figure out that the identity was irrelevant. We've spent 10 years beating our head against escape analysis, trying to reconstruct whether identity was intended or not. And, well, that's basically been a failure, right? We're able to do escape analysis in a lot of the easy cases, and then, there are plenty of times where you do something a little bit more complicated, and then it just doesn't work anymore, and people complain about the fall off a cliff performance. And, we concluded that really what we need is for people to be able to say, this class identity is irrelevant, and you can count on that. So the sweet spot for value types is things that can be passed by value, right? That means small things. Tuples with a few fields, alternate numerics, complex, 128-bit int, unsigned int, big integer, things like that. Algebraic data types like optional or choice. Iterators, where you have a reference into some structure and some indexing information about how far you've iterated through that structure. That's the sweet spot. Something with 200 fields, yes, the VM will let you represent it as a value, but the value of its valueness is greatly reduced by trying to use it in that way. But again, the key motivation is don't force users to choose between things like safety and abstraction and performance. And like a good example of that is optional, right? We added this optional class in Java 8. Very, very useful thing, right? It basically enlists the aid of the type system to prevent you from making null pointer dereferences. That's great, except that it has really kind of an untenable cost, which is you need an extra heap node, you need a box, you need a pointer, you need a dereference. Representing optional as a value type, which morally it was anyway, it was a value-based type, gives you the best of both worlds. You still have the type system working for you to provide safety and abstraction, and then at runtime, the performance overhead is 0 because it's, it just contains a reference that's going to get inlined into whatever the optional is contained in, and it just boils down to bit movement, no allocation, none of that. So we have an open question, which certainly up for discussion in the Valhalla list about is there some degree to which values might want or need polymorphism. We have some ideas about that. I don't want to go into too much detail, but that's one of the topics we'll be discussing for a while. And another big question that we're going to be discussing for a while is migration compatibility. If I have a class like optional in Java 8, which was a reference class, and I'd like to make it a value class in Java 10, can I? Can old call sites continue to work? Can old code continue to compile? This is a pretty important thing because people have been programming in the style like the point class John put up on his slides. People have been programming in that style for a long time. It would be nice to just be able to put value in front of those classes and get all of these performance benefits. So what are the migration compatibility issues there? That's something that we care very, very deeply about. An obvious application of this is, people have been asking for years, where are the tuples in Java? Why can't I have tuples? And with the mechanisms that I just described, tuples fall out like almost trivially. You can represent it using class dynamic where the bootstrap is going to spin a class for, tuple of TUV will have, a field of type T, a field of type U, a field of type V. Two uses of that same tuple of TUV will correspond to the same class because class dynamic types are compared structurally. And so given this VM mechanism, all we would need to add tuples to Java is some way of naming the type, tuple of t and u. That's just syntax. Some way of constructing a tuple from components. I want the tuple of int containing 1 and 3. Well, that's just syntax. And some means of destructuring a tuple into its components. Take this tuple of int and assign the first one to A and the second one to B, and that's, that's what I want, right? So this is what I meant earlier about we want the impedance mismatch between the language model and the services provided by the VM to be as simple as possible, because that's how you get performance transparency. And that's how you avoid all these weird corner cases that come from complex mappings between the language has one notion of a value and the VM has another. Okay, I'm almost done. We've come kind of full circle, to the central problem of language VM coevolution. We don't want to push everything into the VM because that's the wrong way to do it, but we would like for the language and the VM to be in agreement about the general structure of the concepts that we're talking about. We would like the job of the front-end compiler. It may do a lot of type analysis, but it shouldn't have to produce something that looks nothing like the source input. So, the example I just gave with tuples is a good example of how that should work. We're building trivially on general purpose building blocks, and then we can put the bootstrap in the language runtime so any other language can use it if they want, but doesn't have to use it if they don't want, because other languages have tuples, and if they want to use the mechanisms provided, great, and if they want to do it their own way, that's fine too. Okay. So one last thing I'm going to talk about, and this is really just an intro for the next talk, is var handles. Right now, we have a very limited way of dealing with things like atomic updates, like CAS, and fenced updates of variables. Basically, there's this very tight linkage between the way a field is declared and the fencing that we apply to accesses of it. And this is one of those accidental couplings that John talked about earlier. So right now, if a field is volatile, you always get a fence on its access. And if it's non-volatile, you never get a fence on its access. And, concurrency experts may want something a little bit more flexible than that. And so, this initiative, which Paul will talk about, is basically method handles for data, a way of describing access to data that abstracts over the type of the data, abstracts over the location of the data. Is it an instance field, a static field, an array element? Is it off heap somewhere? Don't care. And abstracts over all the access modes, fenced, relaxed, atomic, etc. These are things that we've been doing with unsafe, and we'd like to move them out of the shadowy, underworld of unsafe and out into the light where they're safe and fast. And so you can think of unsafe as kind of an incubation ground for, we dump things there when it's clear that they're useful enough that we need to bring them into the programming model proper. We can do so in a safe and performant manner, and this is sort of a down payment on that particular evolution. So, just to sum up, there's kind of a common theme here, if you caught it, which is more flexible access to data. There's a lot of ways that we talked about pain points in accessing data. Accessing data without indirection. Value types give us the opportunity to flatten aggregates into other aggregates. New arrays give us a way of having a more flexible way of laying out array data in memory, maybe segmented arrays, maybe huge arrays. Maybe sparse arrays. FFI and native interop give us a better way of accessing native data without having to pull it out of the native heap and into the Java heap and relaying it out and all of that and paying all the round trip costs. Generic specialization are kind of like value types for generics. And var handle is having a uniform way of writing code that accesses data in all of these places however you want, right? So, again, the theme is let's stop making programmers choose between the good things like expressiveness, safety, and abstraction, and the accidental things like performance. And with that, we're only a half hour over. Let's do a 20-minute break, and we'll resume with Paul's talk. Thank you very much.